Okay, this is the lecture video for MAC 1140 pre-calculus. We're in section 5.1, and in this section we're going to be taking a look at composite functions, which put in the simplest terms just means that you're substituting one function into another function. We're also going to be taking a look at how to identify the domain of the resulting composite function. So in order to get ready for doing composite functions, we need to just make sure that we have the basic skills of knowing how to substitute, and also that we have the basic skills of being able to identify what makes a function undefined. What are the kind of functions that we actually have to protect from being undefined? And that would be fractions and radicals. Okay, so that'll pop up throughout these problems, but let's start with the basics. Okay, first we're going to do a problem with substitution, since that will be the main skill that you will need just to form a composite function. In this problem, you're being asked to do that, and you would recognize that by the fact that in place of the x, they have substituted a 3x. So that is a direction or an indication that they want you to sub that into the rule for f of x. Okay, so starting here, we're going to take the f function and plug in 3x. So that would be 9 minus 7 times x squared. We're plugging in 3x. You need to square the coefficient as well as the x. That square applies to both of these things, both of these items. Okay, so now it's going to be 9 minus 7 times whatever we get here. That would be 9 when we square it, and x squared when we square the x. So 9x squared. Okay, then applying the negative 7 to the 9x squared, we would end up with 9 minus 63. Negative 7 times 9. 9x squared is 63, x squared. And that would be your final answer. Okay, moving on to the next problem. In this problem, we're seeing if you understand how to tell someone what the domain of a fraction is, because several of these problems, many of these problems, will end up being fractions, and the bottom of a fraction cannot equal 0. So you want to be able to identify the numbers that would cause it to be equal to 0, because that would cause the whole fraction to be undefined. Denominator cannot be equal to 0, and you want to stop that from happening. So when they ask you what is the domain of this overall function, you're basically going to show that you have the skill of knowing what would cause a 0 down here, thereby making the entire fraction undefined, because it cannot belong to the domain. Domain is where you state all the values that it can and cannot be, but by stating what it can't be, you're also simultaneously stating what it can be. So here, the algebra that's required in order to be successful at knowing what makes the denominator 0 is to be able to factor. Okay, when you factor this bottom, this is the difference of squares, and that algorithm for factoring is take the square root of the first term, which is x, and put it in the first position of each parenthesis. Take the square root of the second term and put it in the second position of each parenthesis. The signs are the opposite of each other. One gets a plus, the other one gets a minus. Now you can go after figuring out what would cause this denominator to go to 0. If you cause this factor to go to 0, the whole bottom is 0. Because if this is 0, this being a factor of this, they would get multiplied together, turning the whole denominator into 0. Likewise, if this factor goes to 0, it'll cause the whole denominator to be 0. So x cannot be negative 3, because that would 0 out what's in the first parenthesis. And also x cannot be positive 3, because that would 0 out this factor. And either one would cause the whole denominator to be 0. You can put both of those right here, separated by a comma. So in essence, you are saying that x could be anything except it can't be these two. This is red. X is such that x cannot be negative 3 or 3, but can be anything else. Any other real number. I shouldn't just say anything else. Okay, moving on to definition of a composite function. So as I was stating, composite function really just means substitution. You have to get used to the symbolism that requests you to find a composite function. They can either give it to you like this, f composed of g. Sometimes they write the x and sometimes they don't, but if both of the functions you're working with contain an x, then you are finding a composition in terms of x. This is read f composed of g. That really means g substituted into f. You are always substituting the inner function, or I can say it another way, the function that comes after the composition symbol. This is the composition symbol. It looks like an open circle rather than a multiple. It's not a dot, it's an open circle. So the function that comes after the composition symbol, that's the one that's going to get substituted into this outer function. So you could call this the inner function. You could call it the function that you're going to substitute into the outer function. You could call it the function after the composition symbol. Describe it in those ways. This same composition request can be written like this. This means f composed of g. In other words, you're plugging this into this. So be looking for them to write it either way. Okay, the thing about the domain. Now, this may be something that you may not understand. I'll read the way it is given in the book, and then I'll reword it for you in a way that you can understand and carry out in the rest of the problems. The domain of f composed of g is the set of all numbers x in the domain of g. So in other words, you must obey the domain of this inner function, the one that's going to be substituted into f, the one that comes after the composition symbol. So you must obey the domain of g. Have to protect that g function. Obey the domain of g, the g function, for which g of x is in the domain of x. Now that is what's hard for a lot of students to understand. What that means is that you must also obey the domain of the newly composed function, the function that you're going to create through composition. Okay? All right, so we'll be using that as well. Okay, let's continue with this. Now, we're going to start with some compositions that are built in terms of numeric values. In other words, instead of starting off with an X there, you're starting off with a number. These are on the easier side. When everything turns to just X's, it will be a little tiny bit harder. But these actually, they're just a little bit easier to think about. The algebra that you're going to do is easier when you start off with some numbers like this. So they're asking you to do this. They want to know if you have a function f of x that's equal to x squared and g of x that's equal to the square root of x plus 7. When you do the composition and then plug in 4, does it come out to be 5? They're asking you, is this true or false? It's a question. So we're going to do f composed of g. This is the easiest way to do it. Evaluate this first. Whenever they throw you a number on that inner function, you are to evaluate that first, then substitute it. That's the easiest way to do it. So g of 4, we're going to take the g function, which is x plus 7, and we are being told to plug a 4 in there. So we end up with 11 underneath that square root. After you get done finding out what this is, you're going to take that value, and now you're going to do f composed of g of 4. Now you're going to carry this out. So we just got a square root of 11 for this, and we are going to substitute it into the outer function. You will always be substituting the inner function into the outer function. It's just that when they start you off with numbers, you can make it easier on yourself by evaluating this one first, getting a number rather than plugging it in its x form. Because another way to do this, which is just longer, is you could substitute this whole thing into this, square it, get an expression, and then plug in 4. This is actually less steps. So working on the inner function first, I got square root of 11, and now I'm going to plug it into f. Now, if you're going to substitute, you need to open up that f function. In other words, put blank spots with parentheses, a blank parenthesis wherever there's an x. Okay, so in the f function, it's x squared. Now that you've opened up the f function, you can go and plug in the value you got for g of 4, which was square root of 11. Squaring dissolves this square root, so these cancel each other. Out comes the 11, and that is your final answer. Now the question was, when you do f composed of g of 4, which we just did here, we did the g of 4 first, then we plugged it into f, we got 11. Is it equal to 5? No, it is not. This is not equal to 5, so this is false. Okay, moving to number 4. Okay, in number 4, they're giving f of x equal to square root of x plus 2. They're giving g of x is equal to 4 over x, and they want us to do f composed of g. So unlike number 3, notice that they don't start you off with a numeric value in the inner function. Okay, they just want you, there's no little number right here. So you can't take that little shortcut of evaluating that first and then just plugging the number in. You're going to have to work with straight functions containing only x. So always remember that you are plugging the inner function, the one that comes after the composition symbol, into the outer function. So it is this function, the outer function, that you're opening up, that f function. So f composed of g, opening up that f function. Here's the f function, and I'm opening it up by putting a blank parenthesis where the x is. Then I'm going to take the entire g of x function, I'm going to plug it right in there in the open spot. Okay, now they didn't make it hard on you. In my math lab, I checked out the answers back there, and they don't make you put this together, so you don't have to go any further than that. In many of the problems, you will have to do that, but since it's underneath a radical and it would just, just be too much, they let it go at that. So that's actually the final answer. So you just took G and you substituted in for F, known as a composition, just a way of combining two functions through substitution. They haven't asked us the domain yet on anything, so let's move on to number 5. In problem number 5, in the outline, they say f composed of g. We're going to give it the name h, and they're saying that this is h, 81 minus square root of 81 minus 9x squared. So they're saying which of the following couldn't possibly be the component functions f and g. So basically, just put another way, they're saying these are called component functions, the two functions that you are composing together in order to come up with this brand new function. They're saying if you were to do f composed of g here, would you get that? One of them that doesn't work out, and one of them it does. So all you can do is try each one. Now, if we find it right away, then we know which one is not the one that works, because only one of these works. They only gave you two choices, so let's try A and see what happens. We're going to do f composed of g. This h that they have is just what they're naming, the composition. So you don't need to really worry about that. Okay, so it's always open that outer function and plug this function right into it. So if we open up the f function using this f function, square root of 81 minus 9 times x, and if we take that function and then plug the g function, substitute the g function right into it, which is just x squared, that's the g function. We're taking that entire function, putting it in the open spot for f, and look what we have, 81 minus 9x squared. Is this the composition that they said it would be? Yes, this came out exactly like this, 81 minus 9x squared. So these actually are the two component functions that could be used in a composition fashion in order to get square root of 81 minus 9x squared. So we already know that this one works. These two component functions work. So therefore this is the one that doesn't work. And you could go ahead and try it, but you will not. When you try to plug this into this, look, if you were to plug 9x right in here, you'd have to square the 9 and the x. You would end up getting 81x to the fourth. Or, sorry, 81x squared. And that's just not what's in here. I mean, we can go ahead and do it. If we were going to do f composed of g, we would be opening up f. Always open up that outer function. So it would be 81 minus x squared. We'd be dumping the g of x function right into that open spot, which would be 9x. But look at what you get this time. You get underneath the square root 81 minus 81x squared. So they're saying which of these two component functions, these two or these two, when you do a composition, cannot possibly result in this. And you can see that this did not. So this is the actual answer. This is the one that cannot possibly work. Okay, moving on to number 6. In number 6 and 7, we look at a different way to do compositions. We are still always going to be working with the inner function first, the one that comes after the composition symbol. Only this time we're going to be doing the problem using a table, which means there really isn't too much work for this problem. You can still show your thought process, just as I'm going to do on this paper, so that you can follow me. You can do the same thing on a test when you're taking a test to show me how you got the answer. Okay, so let's try part A. And don't forget, you're doing the inner function first. Always evaluating the inner function first. So, first step is going to be for you to evaluate g at -1. Okay, when you're doing this on a table, usually any function is going to say g of x. But instead of g of x, you have a 1 where the x is. So what that would mean in a table is to go to -1 for your for your x value. So go to -1 and then go down to the row that has the information for g of x. So what you're looking for is the partner that goes with this. So at -1, g of x value is 0. Okay, next step is to now take the the value that you got, and now you're going to plug it into the f function. So our second step is we're going to be going the f function and using the value that we just got right here, which was 0, and plugging it into the f function. Okay, again, usually functions are written f of x. So when you see a number there, it's because you're supposed to be going to that x value first. So go to the x value 0, down to the row that gives the information for f, and that is -1. So -1 is your final answer. Okay, same thing for part B. You're going to do the inner function first. So first step, what is f at 0? Now we had just done this in the previous problem. It was -1. And then part 2, once you know the value of the inner function, which turned out to be -1, we are plugging it into the outer function. And that's pretty much the theme. It's not pretty much the theme. It is the exact theme that you're going to be following for every problem. So we took the -1, plug it into that outer function, go to the table to get the value. This means go to the x value of -1 and down to the row that gives the g information. So at -1, the G value, the Y partner, is 0. And that's your final answer there. Likewise for part C, we're evaluating G of -2 first. That means we're going to go to an X value of -2 right there, down to the G function. That partner is 3. Okay, so when evaluating at -2, the Y partner on the G function is 3. And then once you know what this evaluates to, the Y partner for this X value is 3. You then go and plug that into the outer function. So step 2, taking that outer function called G and evaluating it at 3. This means go to the X value of 3 and then down to the row that has the values for the G function. So that would be 7. So the final answer there is 7. Okay, that completes number 6. Now we're going to do the same thing, but on a graph. Okay, remember, the theme is work with the inner function first. If there's a value, evaluate that first. And then once you get a value for that, the Y partner, you will then plug it into the outer function. Okay, so here we go with part A. We're going to do G composed of F of -1. The F function is the inner function, so we're going to do this first. Now, what this means, usually you would see an X here when they talk about functions. So they're telling you that this represents the X. So go to -1 on the X-axis. Instead of being on a table where you have a column, where you have a row of X values, now you have a graph that has an X-axis. So you're going to go to this X value on the, you're going to go to this value on the X-axis, which is right here. And then you are going to travel until you see the F function, until you reach the F function. That will require sometimes going up and sometimes going on. So be clear about which function's which. This wavy line is the G function, and this function that looks like a V is the F function. So I'm at -1, and I'm going to travel until I hit the F function. At the point where I hit the F function, I'm at a Y value of 2. So that is the Y partner. And I'm going to put it here. I don't want it to look like the final answer. So that is what F of -1 evaluates at. Then you are going to plug it into the G function. So the next step there would be for you to go G at 2. Okay, this means, and then we'll get the final answer. Go to 2 on the X-axis, so go to 2 and travel until you hit the G function. So go to 2, travel till you hit the G function. You are then at a Y value of 3, and that is the final answer for part A. Okay, instead of using a table, you're using a graph. In part B, we're going to evaluate G composed of F at 0. Okay, we're working on this first. So we're going to go to the X value 0 on the X-axis right here. Travel until you hit the F function. Go to 0 on the X-axis and then travel till you hit the F function. So we're on 0. Travel till you hit the F function. You're at a Y value of 1. So this part right here is equal to 1. Then you're going to use it and substitute it into the G function. So you're going to evaluate G at 1. So go to 1 on the X-axis, travel till you hit the G function. And when you finally hit that G function, you're at a height of 5. And that's the final answer for part B. Okay, part C. Sorry, all these have multiple parts. Don't want to leave you hanging so that you can get the homework done easily. So I'm going to do anything that's in here. So F composed of G at -1. Again, you're doing this first. Okay, when you go to -1 on the X-axis and travel until you hit the G function. So go to -1, travel till you hit the G function. You're right there at the edge of it. You're at a height of 4. So this is equal to 4. You're just looking for the Y partner that goes with that. Then you're going to evaluate the f function at 4. You're going to finish the problem like that. So go to 4 on the x-axis and travel till you hit the f function. So that would bring you right here, y value of -3. Final answer for part C. Okay, moving to part D. So in part D, we're doing f composed of g at 4. F composed of g at 4. We're doing this first, so go to 4 on the x-axis, travel till you hit the g function. 4, travel up to hit that g function, finally hit it right here, glance over at the y-axis, you're at 3. So this is equal to 3. And then you're going to plug that into the f function. So it's f evaluated at 3. So to finish this off, it would be go to 3, come down to hit the f function, and when you do finally hit it, glance over at the y-axis, you're at a depth of -2. Okay, so that completes all the way up to example 7. Okay, now we're back to some functions where again they're starting you off with numbers, but instead of using a table and instead of using a graph, you're doing it right in the function. So just be aware that they can present it to you in 3 different ways. They can ask you to do a composition with a table, with a graph, or with the actual functions themselves. Now they happen to be giving you numbers here, which as I stated earlier in this section, that makes it a little bit easier than if they hadn't started you with these numbers. Okay, so here we go, part A. We're doing always the inner function first. So we're going to do g of 4 first, see what that turns out to be. Got to go grab the g function. You have no table and no graph to get it visually from, so we're going to go 15. We're going to plug that 4 in right there and add 5. Okay, this gives us 15 over 16 plus 5 is 21. When you get finished with that part, don't forget that you are taking the value you just got here, which is 15 over 21, and evaluating the f function at that value. Okay, so you just take this, plug it right in here, plugging 15 over 21 into the f function, and the f function is nothing more than absolute value of whatever you're plugging in. Absolute value really just means how far is this number, what is the distance of this number from 0? That's why it always comes out positive, because distance is considered a positive type of positive concept. You don't tell someone, oh, I live -10 miles from the school. Distance is always positive, and that is what absolute value means. So this is just 15 over 21 as you release it from the absolute value bars, applying the definition of absolute value. Moving, and that's the final answer. Because we did the inner portion, then we took what we got and plugged it into the outer function. Moving to part B. This one we're going to start off with f of 2. So grab the f function, which is just absolute value of 2 is just 2. And once you get that answer, you're going to plug that answer into the g function. So it's the g function. You're taking that answer you just got and plugging it in. G function is written as 15 over x squared, which is 2 plus 5. And that's equal to 15 over 4 plus 5, which is 9. And before I go, saying that this is the answer, let me fix this, because they are going to want it reduced. They're not going to let you give the answer reduced, so let me actually box that off as the final answer. So we got 15 over 21. Don't forget to reduce it. So 3 goes into the top 5 times, 3 goes into the bottom 7 times. So that would be the most reduced form of the answer, and that's the one you want to get. Okay? By 3 divided by 3. Okay, here I got 15 over 9. This one also divides by 3 on top and bottom. 3 goes into the top 5 times, 3 goes into the bottom 3 times. And that's the final answer there. Moving to part C. In part C, you're doing F composed of itself at 1. Okay, so just like what I've showed you in these previous problems, you're going to do the inner portion first. So the F function with a 1 plugged in would be absolute value of 1, which is just equal to 1. And then as soon as you get done with that, you're going to take this 1 and plug it into the F function again, and you can see what you're going to get probably already. But if you're going to take this and plug it into the F function all over again, you're going to get the same thing. So this would be a 1 in the F function, which is this absolute value of x, and what we're plugging in there is a 1. So final answer here, 1. I'm going to do part D up at the top of the paper because I'm running out of room there. Okay, so part D for this problem, I'll do it up here. Okay, so in part D we're doing G composed of itself. And you don't always get the same value the first and the second time. This was just turned out like that in that particular problem, but let's go ahead and do this one. We're going to do so that you can see that you don't always get, just because you're doing a composition of 2 functions in and of themselves, you don't get the same value both times all the time. Not all the time. Okay, so we're going to do G of 0 first. Doing that first. And when you do G of 0, you're plugging 0 into this G function, so it would be 15 over 0 squared plus 5, which is just 15 over 5, because 0 plus 5 is just 5. Whoops, I wrote 3. I'm already thinking of the answer. So that's 3. And then as soon as you get done with that, you're plugging whatever you got here, which was just a 3, you're plugging it into the outer function. So now you're going to do G composed of 3. And the G function is, again, once again, 15 over x squared plus 5. 15 over x squared this time. You're plugging in this 3 right there. That's what that means. So 3 squared plus 5. So this ends up being 15 over 9 plus 5 is 14, and that doesn't reduce. That's the final answer for part D. Okay, pretty tedious, but you're going to have multiple parts in my math lab, so I want to make sure and give you good exposure to that. Now we're going to get into the skill of being able to tell what is the domain for the composition. So remember, when you do these functions, you're going to, when you go to state the domain, you're going to obey the domain of the inner function. That's what I'm going to call it, but I could describe it other ways. You could call it, this would be the inner function, or you could, it's the function after the composition symbol. It's what you're substituting into the outer function. So obey the domain of the inner function. That's one thing you have to pay attention to when you're deciding on the domain, the final domain of your composed function. And you also have to obey the domain of the composed function. Sorry, I got to abbreviate here. We don't have much room. Okay, here we go with part A. We're going to do F composed of G. Okay, remember, we're always, now we don't have any numbers to work with first, as we did in this previous problem, where they gave you all of these numbers attached to the inner function. So the shortcut is to evaluate that inner function at 4 and then just take the number and plug it in. That's a lot less cumbersome than when you have to work with x's the whole way through. But we are forced to have to do that in this problem, so we'll just deal with that. We're plugging this always into the outer function. Okay, so that means you have to open up the outer function. Anytime you're going to plug anything into another function, you have to open up parentheses that are blank wherever there was an x. Okay, so we're going to open up that f function, which is x squared. So it's x squared. We are plugging g into f. Now the g function is x squared plus 7. This will give you a chance to practice those shortcuts for foiling. I know some of you are still going x squared plus 7 times x squared plus 7, then drawing the 2 arrows from x squared, drawing the 2 arrows from 7. And after drawing that all out, you're finding 4 products, combining the like terms, and you're up to 6 steps by then. Actually, it's 7 steps. So by the time you draw the parentheses twice, that's 7 things that you've done. We're going to do it in 3 steps. And that shortcut, you have to memorize what shortcut goes with what kind of foiling. We are foiling out a binomial. In other words, we're multiplying a binomial times itself. We're squaring a binomial, and that is the square, double, square shortcut. You don't have to write anything out. You jump right into the answer where the terms will already be combined. So first time you square, you're squaring this. So x squared times x squared, that's what squaring is. Multiplying a term by itself would be x to the 4th. When you double, that means multiply this times this, so that 7 would be in front of here as a coefficient, but then double that coefficient, it would be positive 14x squared. And then when you square the second time, you're just squaring the number. Anything that comes from squaring is positive. That's why the front and the back terms are positive. This middle term will always have the sign that's in the parentheses. So there it is. It's already all squared out when you do f composed of g. Now, hold on one second. We were supposed to open up f, which was just x squared, and we were supposed to plug in, I just want to check this, we were supposed to plug in x squared plus 7. We did that here. We went and squared this binomial using square, double, square. So that's what we get. Now let's talk about the domain, and specifically, let's talk about this comment that I gave you when I gave you the definition of a composite function, where they also talked about the domain. Okay, so notice that if we obey the domain of the inner function, look at the inner function. It is called g. Look at what it is. This is a polynomial. It does not have a fraction in it because fractions need to be protected. You can't allow the denominator to go to 0. So you have to stop the user from plugging in anything that would create a 0 denominator. But we don't have to worry about that because this is not a fraction. It's also not a radical because radicals can be undefined in the real number system if you let them go imaginary. That happens when you plug the wrong kind of numbers into a even radical. Even radicals are square roots, 4th root, 6th root, anything where the index is 2. Well, this isn't a radical. So when it's a polynomial, it's not a fraction, it's not a radical. That means that the domain of the inner function, which happens to be called g, and once again, this is the g function. It's just a polynomial, therefore the domain can be any real number at all. There are no restrictions on it. I also said that you need to obey the domain of the composite function that you just came up with. So the domain of this new function that we created through composition, x to the 4th plus 14x squared plus 49, that's also a polynomial that is not a fraction and it's not a radical. So its domain is also all real numbers. Therefore, final domain is X can be any real number. And in my math lab, it's probably for an answer like that, since they don't have this symbol for all real numbers in there, it'll just be a pull down menu where it will be in sentence form and it'll say X can be any real number for the domain. Okay, moving to part B. Now you're going to see that what I just spelled out for you here, domain of the inner function being all real numbers, domain of the resulting function being all real numbers, it'll be because they're both polynomials. So that same line of reasoning is going to be true in all four parts here. Okay, G composed of F, doing part B now. In part B, we are opening up this function right here. Always open up the outer function and plug this one into it. Okay, so let's see. My G function is x squared. I'm opening it up by putting a blank spot where the x is with a square on it, plus 7. And into it, you're going to dump the entire f function, not the name of it, the actual function rule. So put that right in there. When you take x squared and square it, take a power raised to another power, you multiply the powers. So this is what I get as my composite function. Notice again that the original function here, I'm not going to write it out all three parts each time, but I will point to it. The inner function was f. It is a polynomial that does not happen to be fractional, and it is not part of a radical. Therefore, the domain is all real numbers for f. I guess I'll write it for just one more of them. The domain of that inner function, all real numbers. The domain of the newly composed function, which is this x to the fourth plus 7, that's also all real numbers because it's a polynomial that's not a radical or a fraction. So in the end, final domain for part B, all real numbers. There are absolutely no restrictions here, no restrictions here. And when that's the case, the final domain for the composed function is all real numbers. You always just have to consider, and we haven't gotten anywhere there's been any restrictions, you always have to consider, in addition to the newly composed function, you have to consider what you made it out of. So that would be this inner function and whether or not it has any restrictions. Okay, part C. Part C, we're doing f composed of itself. So we're going to open up the f function and plug in the f function. Okay, so opening up that f function, which would be x squared, and dumping in here the f function again, which would be x squared. So for this particular problem, in number 9, when you go to do part C, you get x to the fourth. This power of 2 raised to a power of 2 again. Okay, notice that the domain of this newly composed function, it's a polynomial. It's not a radical, not a fraction, so it's all real numbers. And if you look at the domain of the inner function, which was f, same thing. It's a polynomial, but it's not a fraction or a radical, so the domain of that is all real numbers. Therefore, this is the final domain, all real numbers. And I am considering two things each time I come up with that final domain. Part D, I'm going to do G composed of G. Okay, so I'm going to open up the G function, which is x squared plus 7. And I'm going to take the G function and plug it right in that spot again. So this is x squared plus 7. You're going to use square double square here because this is a binomial, two terms, and you're trying to FOIL it out. When you're taking a binomial and multiplying it by itself, which is what square means, you're FOILing. Okay, use this to go from 7 steps to 3. So you're going to square this. That means x squared times x squared is x to the fourth. Then you're going to double. You're going to multiply this times this. So imagine having this in front of it as a coefficient, but then doubling it. In other words, multiplying by 2. So you'd have 14 x squared. And then you're going to square again with the 7, which would be 49, and then there's this additional 7 here. So when you combine the two constants at the end, you have x to the 4th plus 14x squared plus 56. And again, by the same reasoning that I went over through parts A, B, and C, the domain, final domain here, is all real numbers. Okay, that's the final domain for that composed function. And I am taking into consideration, but I've gone through the reasoning a few times, so I don't really think you need to hear it again. Okay, now let's get to some problems where figuring out the domain is a little tiny bit more intense. You have to give it more consideration because now you're into fractional territory. So you have to really think about what makes it undefined. For polynomials, there is nothing that can make the polynomial undefined. Okay, so here we go. We're going to do part A. I'm probably only going to have room to do part A right here, so then I will do the rest of them, parts B, C, and D. Just bear with me. I know it's a lot of parts, but it'll do you well when you go to do the homework. I'll have to do parts B, C, and D on the back. Okay, so here's part A. Okay, so part A, we're going to do F composed of G. Throughout this outline, I have stressed that you are always opening up this function, and you're taking the inner function and plugging it into that function. So, opening up F. This is F. It's 8 over x minus 3. And in that blank spot, we are going to be dumping. We're going to take the g function and substitute it into this open spot in the f function. G function is 9 over x. Okay, situation here is that this is for number 1, it's a complex fraction. You have the main fraction here with a numerator and denominator, and then you have this other fraction with a numerator and denominator. And you cannot give an answer like that. That needs to be simplified. So if you have any shot of simplifying this, you're going to need to pull these two terms together. You have to combine them. So when one of your terms is a fraction and the other one is not, you need to think of it as a fraction and make it have the same denominator. Otherwise, you cannot combine these two terms through subtraction. So if this denominator is x, you want this denominator to be x. You change the denominator through multiplication into what you want it to be. Whatever you are multiplying the denominator by, you multiply the numerator by. So I'm trying to get these two terms right here to have the same denominator. They now do. Let's rewrite this. So we have 9 over x, and then we have negative 3x over x. Okay, and because they now both have the same denominator, we can pull them together into a single fraction. You must have a single fraction in the denominator to simplify this complex fraction. So it's 9 minus 3x over a common denominator of x. Once you get a single fraction in the denominator, you can look at the alternative definition for division. This says 8 divided by this. Well, division is the same thing as multiplying by the reciprocal. In other words, take all of this, float it to the top, and multiply by the reciprocal of this divisor. So now, instead of having a divisor of 9 minus 3x over x, it has now floated to the top, acting as a multiplicative reciprocal. So that's not there anymore. And what you end up getting is 8x over 9 minus 3x. Okay, now let's try and do the domain. Okay, remember there are two considerations. You need to obey the domain of the inner function as well as obeying the domain of the newly composed function. Okay, so let's do that. First, let's do the domain of the inner function. Okay, looking at the g function, we see that the only thing that would make this undefined is if x was equal to 0. That would make a 0 on the bottom, thereby making the whole fraction undefined. So for the g function, x cannot be equal to 0. It can be anything but 0. Now, let's do, and I meant to put here, fix this, obey the domain. So you can understand it when you're reading. I think that might help. You need to obey the domain of G. And we also need to obey the domain of the newly composed function that we came up with, which is 8x, so I'll write that here, 8x over 9 minus 3x. That is the new function we got when we performed the composition. So what could make this fraction undefined? Again, anything that makes the denominator 0. It is only the denominator that needs to be protected. So I really want to know what would make this 0. So you can just come over here and do a quick setting it equal to 0 and find out what makes it 0. As soon as you solve it, you're going to know that. Okay, you could leave the negative 3x right there and bring this over here. Then you would have negative 3x equal to negative 9. You could then divide by negative 3, divide by negative 3, and you figure out that x is equal to 3. Well, that's actually what x can't be. And you may have been able to see that just by looking at this. If that's the case, that's fine, because you've already done so much work that would certainly suffice as work, the other things you've done. So look, when you put a 3 in there, you'd have 9 minus 9, and that would cause a 0. So that is a value that x absolutely can't be. So in the grand finale of things, the final domain is, the domain is the set of all x values such that x cannot be equal to, let's see, 0. It can't be 0, and it also cannot be equal to 3. That's your final domain. They will start you off with this in My Math Lab. You'll be able to type an X from your keyboard. This symbol will be available in My Math Lab, and then you'll state the values that it can't be. Okay, now I've already run out of room here, so I'm going to have to do parts B through D on the opposite side. Okay, so here's B. We're doing G composed of F. And I'll just put those functions up here at the top of the paper, so me for one thing so you could start, you're going to probably need to write this out somewhere also so that we can be looking at them as we do the problem. So one more time, f of x from the previous page was 8 over x minus 3, and we're also working with this function called g, and g is just 9 over x. Okay, so in this part they've asked us to plug this into this. You're always substituting inner function into the outer function. So you always open up that outer function. We're opening up the g function, so it's 9 over x. And in that blank spot, we're going to put the f function, which is 8 over x minus 3. Okay, now lucky for us, there is no extra term added here that needs to be combined with this fraction. You have a single fraction in your denominator, so you can take this complex fraction. You got this big fraction where 9's the numerator and this is the denominator, but you also have this other fraction where 8's the numerator and x minus 3 denominator. So to turn this into just one fraction, you float and flip. You're going to float this up to the numerator and allow it to act as a multiplicative reciprocal. Just don't forget to flip it over. Float and flip. By the time you float it to the top and flip it over, you no longer want to look at that. So now it'll be 9 times x minus 3, and your denominator is 8. And you do want to get rid of that parenthesis. Go ahead and multiply this 9 times the x as well as the negative 3. Over 8. So that's your composition. I think the harder part is, you got to think about the things that are in the domain. It concerns two parts. You have to obey the domain. You don't need to write the word obey. We're obeying the domain of the f function. Okay, the f function. Let's see. Let's look at that. The only thing that would make this undefined is if you put a 3 in for x. So x actually cannot be 3 because it would create a 0, thereby making this fraction undefined. So it can't be 3. And then we also have to obey the domain of the newly composed function, which is 9x minus 27 over 8. Okay, if we obey that kind of function, remember, our job is to look at what we're trying to find the domain for and make sure that the denominator does not go to 0. So, I don't need that equal sign. Notice that there's no variables down here, so there is no way that this bottom is ever going to be 0. So you can actually, for this newly composed function, you can use any real number you want. So this is the domain for f. This is the domain for the newly composed function. And the final answer for the domain, it's x is such that x can be anything, but except it cannot be 3. It can be just about anything, but it can't be 3. This didn't impose any other restriction, so we only have to worry about that one restriction. Okay, moving to part C. In part C, we're going to be doing f composed of itself. We have our functions right there above, so we're going to be opening up the f function and actually plugging the f function into itself. So the f function is 8 over x minus 3, opening up a blank spot where the x was, and now dumping in the f function again, which is 8 over x minus 3. Back to the difficulty we had in part A, where we had a fraction that we needed to combine with something that wasn't a fraction. So very easily you can think of it as a fraction. You need this denominator to match this. So this denominator needs to be x minus 3 just like that. So it's easy to change a 1 into whatever you want it to be by just multiplying by what you want it to be. When you are multiplying the bottom of a fraction by something that did not exist in the original fraction, you must multiply the top. You don't have to write this bar, but you must multiply the top and the bottom by the same quantity, so that in essence what you're really multiplying by is something over itself, which is just a 1. So it doesn't really change the value, just the form. Okay, continuing to work with trying to simplify this. So we have 8 over x minus 3. Well, both of these have a denominator of x minus 3. We could just jump right into this step. They both have a common denominator now. And once they have a common denominator, you just write the common denominator and do no further work on the bottom. But the tops, that needs work. We have an 8 as the numerator for that one. And then here it is, be careful with this, it's negative 3. That negative goes with the 3 and gets distributed to the x as well as the negative 3 in the back. And a lot of students would fall there. They would forget to carry the negative with the 3. Some of them forget to multiply by the back number. So it's negative 3 times x, negative 3x, negative 3 times negative 3, positive 9. Okay, almost there, almost ready to float and flip. Working on getting that single fraction. It's 8 plus 9, 17, minus 3x over x minus 3. Once you get a single fraction on the bottom, you can go from having a complex fraction, a fraction within another fraction, to just a single fraction by doing this. Bring this, so instead of division by this fraction, you turn it into what's equivalent, multiplication by the reciprocal. x minus 3 over 17 minus 3x. So I just took this and flipped it over, so now it's at the top. And then to finish it, it would be 8 times x minus 3, so you have to multiply that 8 by everything over here, which would be 8x minus 24 over 17 minus 3x. So there is your newly composed fraction in its most simplified form, and the form that you are going to be required to come, you're going to be required to get to that point before feeding in your answer. So you need the skill of being able to simplify a complex fraction. Okay, let's work on the domain. So again, when you're doing the domain, you have to obey the domain of the inner function. Okay, inner function was f of x. There's f of x right there. Only thing that is not in the domain is 3. 3 would cause a 0 here, thereby making this undefined. So x cannot be 3. Okay, then we also have to obey the domain of the new function that we created, which was 8x minus 24 over 17 minus 3x. We need to know what would cause a 0 in this denominator. So let's figure out what that is. What would cause this to be equal to 0? Okay, we could leave the negative 3x here. We could bring this 17 over to the other side, which would make it negative 17, and then divide by negative 3. This would be 17 over 3, and that is the number that x actually can't be, because if you were to put that right in here, you would have 17 minus 3 times this, which would turn out to be 17. 17 minus 17 would be 0. No good. So for this particular this newly composed function, x cannot be 17 over 3. Final domain for part C. Final domain, whoops, sorry about that. I should have slid that up. Anyway, let me go over this a little bit. This is what I got for the newly composed function. I then wanted to find the domain. So again, remember, it's always two things that you're considering when you try to find the domain of a composition. Not only are you looking at the composition, but you're also looking at the domain of the inner function. This is the inner function, which is the function that comes after the little compositions bubble. So in the f function, you said x cannot be 3. And that's why I have this comment right here in the f function, x cannot be 3. This was my newly composed function. I wasn't sure what would make this 0, but I knew that I couldn't use it, whatever it was, so I just set this equal to 0 to figure out what the value is that would make it 0. That turned out, when I moved the 17, to be negative 17 divided by negative 3, positive 17 over 3, because those negatives cancel. So that is the value that it can't be. In the end, I'm going to throw both of these restrictions into my final domain. So x is such that x cannot be, doesn't matter which one you put first, 3, and it also cannot be 17 over 3, and that's the final domain for C. Okay, last part, very strenuous, this problem. Last part, we're trying to do G composed of G. Okay, so let's see. That means we're going to open up G. G function is 9 over x, and we're going to plug that same G function right into that open spot, 9 over x. This one is easier than part C and part A because there's no additional term being added or subtracted like there was in the previous part that we just did, part C, which also happened in part A. So you're already at the stage where you have a single fraction and you can just go right into that step where you float and flip to go from a complex fraction to a single fraction. So float this divisor up to the top. It now becomes a multiplier, but multiplication by the reciprocal. That's what division is equivalent to. So this is not here anymore. These 9's cancel because this one's in the numerator and a matching number in the denominator, leaving you with just x. Okay, then there comes, so this is my composition right here. Then there comes the part where you're trying to figure out the domain. So the domain, consider the inner function. And for the inner function, once again, look at g of x. The only thing that x can't be is 0. So there's the restriction for the g function. And then also look at the domain of your newly composed function where we just got an x. This is the newly composed function. It's a polynomial, which is not a fraction, and it's also not a radical. That means that x can be any real number that you like. When you combine these two, the final domain, you have to mention any restrictions that occurred here or here. We only have restrictions in this case, so no additional restrictions there. So x is such that x cannot be 0. Whew, out of breath. Number 10. Okay, this is the last problem, number 11, where it says you have two functions and you want to do f composed of g. They're just giving it the name h, and they're saying that the composition, which they're calling h, that it should look like this. Then they give you 4 choices down here where you have what's called component functions, the functions that you're going to use to do the composition. An f and a g here, an f and a g here, f and a g here. And they want to know which 2 functions in choice A, B, C, or D would result in this composition if you're doing f composed of g. Okay, now you can try all of them if you want. Sometimes you can tell visually how it would be possible to get 4x plus 2 to the 9th power. You can still show something no matter what. I mean, I'm eyeballing part D. I know that I want a 9th degree on there. This has a 9th degree, and I see that the inside of it, underneath the 9th degree, should be 4x plus 2 as the base, and this would be perfect. Because if you did f composed of g here, you'd be opening up this f function like we always do. We always open up that outer function. In other words, we just leave a blank spot where the x is, but attach the power of 9. And we would dump in the g function into that open spot. And hopefully you can see that that did result in the exact composition that they were looking for. If you were to try any of these other ones, I'm not going to try them all, but if you were to try any of these other ones, you just wouldn't result in 4x plus 2 to the 9th power. Like for instance, if you did f composed of g here using these 2 component functions, you'd be opening up the f, so you'd be going x minus 2 over 4, and you'd be dumping in the g function. You'd be dumping this into the open spot, that g function being 9th root of x. Well, that just simply is not this function that they were looking for. And in a similar manner, the same thing would happen if you did the composition using these 2. If you did, I'll just do this one. I'm not going to do all of them. This is practically all of them. If you were to do f of g as instructed using these component functions, again, you'd be opening up f. So 4x plus 2, and you'd be dumping the g function into this open spot, which is x to the 9th. So what do you end up getting? Make this look more like a power. If I can write a little better, it would be 4x to the 9th, 4 times x to the 9th plus 2. Well, that just isn't what they wanted you to get. When you did f composed of g, they wanted you to come up with this function called h, which looks like this, and that certainly isn't that. So that doesn't work, that doesn't work. Likewise, b wouldn't work. Choice D is the answer. Okay, that concludes section 5.1.